Yeah, so we are going to look at mechanisms. Last week, we looked at balancing of rotating masses, and then we solved some problems, and I gave you some assignments. We'll move on to the next chapter, which is mechanisms. Yeah, so basically, we'll look at the definitions of what a machine is, what a mechanism is, what a link is, what a joint is, and what an actuator is. All those ones form part of what we call a machine. But a mechanism is also part of a machine. So let's look at, first of all, the definition of what a mechanism is. So when we talk about a machine, we say a machine is just what? A mechanism or a collection of what? Mechanisms, which are capable of what? Transmitting a force from a source of power to the resistance to what? Overcome. And mind you, we said that for machines, their job is to just what? Transmit a force or even transmission of what? Motion. Uh, so if we have so many mechanisms that have been what? Put together to perform a particular function, then we say it is what? Called what? A machine. Hmm? So maybe we have a force to overcome at one point. We might need one or two mechanisms which must be what? Put together so as to be able to what? Overcome that load at that point. Or sometimes too, we want to transmit motion from one point toward the other. What we do is we put one or two mechanisms together, depending on what we want to do, and then see how best those mechanisms can work together to transmit that motion from the source of power to the other. So we say if the forces are associated with high temperature, then we say we say we have what we call an engine. So in effect, we say an engine is a collection of what mechanisms that transmit what motion or a force from a source. But those forces or those motions are associated with what? High temperatures. So those of you who know, who have seen an engine before, realize that we have a fuel and then what? The admission of air. And then we have an ignition source. You see. So if the fuel and the air mix together and then that ignition source ignites, then we have what we call what? Burning. And when the fuel starts burning, it generates what? Energy. And that energy is what you use to what? Drive what? The crankshaft. And the crankshaft will drive the pistons. And then, in effect, the crankshaft that is rotating will what? Rotate the wheels of the vehicle, and the vehicle will what? Move forward. So we say when those forces are associated with high temperatures, we no longer call it what? A machine, but we say it is called what? An engine. So we take note. Now, what is a mechanism? We have looked at the definition of a machine, and we said that a machine is basically made up of a collection of mechanisms. Now, what is mechanisms? A mechanism itself. We say a mechanism can be considered to be what? A rigid part. And if we say a rigid part, then in fact we are trying to say that that body doesn't what? Deform. Your basic mechanics. So any rigid body doesn't what? Deform. And they are not only rigid bodies, but they are arranged and connected, you see, such that they can produce what the desired what motion of the machine. Mind you, we said that the machine transmits has one or two mechanism or a collection of mechanisms to transfer power from one source to the other. Now, a mechanism we say they are rigid parts that are arranged and connected such that they can produce what the desired motion of what the machine. That means that every machine has its what is designed for a particular purpose, you see. So if the purpose of the machine is to maybe move a vehicle forward or something, then it means that the mechanism should be able to what? Carry out that purpose. That means that we don't actually design mechanisms for design's sake. Whatever we design, we make sure it has what? A particular function that it must what? Perform. So we say a mechanism therefore consists of connected parts, and the main objective of those connected parts is what? Transmission or transferring motion and forces from the power source to the what? Output. So you take note, the figure beside it shows a mechanism. The straight lines here are what we are calling the links. And where we have this circle is called what? The joints. And you realize that the link here is fixed, you see. And if you look at this link, it is what? Oscillating from left to right. And then the joint there is what? Rotating, you see. So if we have such a mechanism, then we can actually say that this mechanism can actually carry out what? The purpose for which it was what? Designed for. Any question up to this point? Now we said that we have what we call what? Links. Agreed. Now what are links itself? So these rigid parts that we defined when we were defining mechanisms are what we are calling what? The links. That means that we have a machine, and a mechanism forms what? A part of what? A machine. Now the links too will form part of what? A mechanism. So we say links are the individual parts of what? A mechanism. So if you take this mechanism for instance, we will say we have 1, 2, 3, 4 links. So those 4 links will be connected together such that they can what? Produce the desired motion, or they can transfer what? Motion and force from the power source to what? The output. So these links we say are connected in a manner that it can what? Transmit motion from the input link to the what? Output link what? Follower. That means that we have what? An input link as well as what? The output. So the input will take the source from where? The engine. And then the output will transmit the motion from what? The input link to the what? For the motion to be what? Transmitted. You see. So we have so many different types of links. And the examples are the lever cranks, the slider shaft, pistons. We see all of them are what? Links. We have also connecting rods. We have pulleys. All of them, we classify them under what? Links. And basically, we have 2 types of links. We say the 2 types are called what? A simple link and then what? A complex link. What is a simple link? What is a complex link? We say a simple link is what? A rigid body that contains only 2 joints, which connect it to another what? Link. E.g., a crank which is simple that is able to complete a full rotation about what? A fixed what? Point. So we say for this one, for instance, if we say from this point up to this point is the only link that we have, then we say this is called what? A simple what? Link. But if you consider the other links in addition, then we say it is what? A complex what? Link. So we say a complex link is what? A rigid body that contains more than what? 2 joints. So the main difference between a simple link and then a complex link is what? The number of joints what? Available. If you count the number of joints and you have 2, then you can say, okay, for this mechanism, it has what we call what? Simple links. If you count the joints and they are more than 2, then we say for this mechanism has what we call what? Complex links connected together. You see. So examples of motions are the sliding. When we say sliding, we mean an example is what? A piston in what? A cylinder. Whereas when we talked about engines, we said we have pistons that are what? Reciprocating. When we meet on Friday, I will try and then bring the simple engine for us to look at it and then see how that mechanism works is achieved. So when we meet on Friday, we'll look at what a piston is. And even another one is what? Turning. And an example of a turning motion is what? A crankshaft rotating on what? Bearings. And then we also have what we call what? A screw motion. And an example of that is what? A nut and what? A bolt. So all those ones are examples of what? Motion. Huh? So on Friday, we'll look at what a piston is, what a crankshaft is, and how those what are connected to achieve what we call, to achieve the desired motion in engines. So we have talked about the fact that a link is what? It's made up of what? Two. That is, we have the simple link, which is made up of two joints, and then we have what? The complex is made up of what? More than two joints. So we look at what a joint is, so that if we are told to classify a link, we can easily know what we call what a joint. Because if you know a joint, then we can know whether we have two joints, three joints, 4, 5, and so on and what, so forth. So we say a joint is what? Just a movable connection between links and allows relative motion between what? The links. You see. And we say the joints two are divided into two. We have the primary what? Joint. And then the primary joint, we can say they are also called what? Four joints. The primary joint, we can say they are also called what? Four joints. And then we have what we call the higher order joint, which we can also say they are called what? Half joints. And then the four joints are divided into two. That is the referring what joint, or what we call the pin or hand joint. And this type of joint allows what? Pure rotation between what? The two links that it connects. And then we also have what? A sliding joint. An example is the piston or what? The prismatic joint. And we say this allows what? Linear motion between what? The links that what? It connects. You see. So basically, when we talk about four joints, then we are talking about whether the joint is what? Allowing rotation, or it is allowing what? Sliding. Eh? So if that's the case, then those two are classified under what? Four joints. And then the higher order joint or half joint, that one they allow for what? Both rotation and what? Sliding. You see. So four joint allows for only one word, either one of rotation or sliding, but half joint allow for both. We have some mechanisms where we can say they undergo both what? Rotation and then what? Sliding. So if we have such a case, then we say it is no longer what? A full joint, but what? A half joint. Because it undergoes what? Half rotation as well as what? Half sliding. So those are basically the two main types of what? Joints that we have. And an example of a half joint is what we call what? A cam, and then the follower. And also the gear, we also classify it under what? A half joint. So if you have a mechanism made up of a cam, then you should know that automatically the cam will have what? A half joint. You see. A gear too, we say, is also what? A type of what? Half joint. Because what they both have in common is they allow for what? Both rotation and then sliding at the same time. Now we have looked at machine, mechanism, link, and then joint. The last one we'll look at is the actuator. And what's an actuator? An actuator, we say, is that component that drives what? The mechanism. You see, the actuator, we say, will be the heart of what? The mechanism. Without it, the mechanism cannot what? Operate. So we have common actuators, and that include motors, engines, cylinders, ball screw motors, and then what? Solenoids. All those we classify them under what? Actuators. So whenever you pick any machine, by all means, that machine will have what? A mechanism. And that mechanism, that machine too, when we break it down, we will say we have some links and then some joints. And at the heart of that machine is what we call what, the actuator. Without that actuator, the mechanism will become what, useless, because it is the source of energy of what, the mechanisms. That's why whenever you see any machine, it's either the machine has a motor, it has an engine, or it has what, a hydraulic or pneumatic component, or it even have what, ball screw motors or solenoids. Every machine will have at least one or two of what, these actuators. But we also see we have manually operated machine what, actuators. Normally, those manually operated are called what, the crank. Uh, that one too, we can say a crank is also a what, an actuator. Remember those days, whenever you want to start a generator, you will see you have to start it manually. Those days, until recently that we have automatic generators where you can easily start it by what, just turning a knob. But those days, you have to what, crank it manually before the generator can what, start. And so we can say a normal crank tool is also part of what, an actuator. So you take note. Any question before we move on to what we call linkages? Any question on the definitions of machine, mechanism, link, joints, and then actuators? If you have any question, you just
is it the turning of? Hello.
Hello, yeah, I'm listening.
Hello,
yeah, I can hear you.
So I'm asking, is it the turning of? That process is the actuator. The person turning the crank is the acting as the actuator, or the crank.
The crank itself is the one that is acting as the actuator. Because you, the human being, you are not part of what, the machine, you see. So you apply that force to turn the crank, and the crank will in turn what, turn at the other parts of what, the machine. So we say the crank is what, the actuator, and not what, the human being. Is it clear?
Yes, please, it is.
Oh, okay. Any question on the definitions? These definitions are very important, so you just have to note them. You can be asked to differentiate between them, so you take note of them. So if you have any question, just ask so that we clarify it before we move on to one other aspect, which is called the linkages. I can box on.
Hello, sir. Hello. Sir, I'm asking that. Hello.
Yeah.
Yeah, I'm asking that. So anything that provides
I can't really hear you well. Mature your voice.
I'm saying that anything that provides the. So in terms of motor like this, you are able to see that the electromagnetic connection.
I can't hear you. Hello. Hello.
Sir, please, can you go over the 4 joints and a half joints again, and the cam joint?
Yeah, the full joint, we said that the full joint normally connects what? One routine, one what? Movement. You see? And that movement can either be what? Rotation, or it can be what? Sliding. So if maybe the mechanism allows for only sliding, then we say it is called what? A full joint. Or if the mechanism allows for only rotation, then we can say it is called what? A full joint. But in a scenario where that mechanism can allow for both what? Sliding and then what? Rotation, then we say that mechanism is no longer what? A full joint, but it is what? Having what? A half joint, you see. Because it can behave as what? Either it can behave as if it is rotating, and at the same time it can behave as if it is what? Sliding. So we can't actually say whether it is sliding or it's rotating. So you say, let's put it together and then call it what? A half joint. You see. So that is what we mean by a full joint and what? A half joint.
Yeah, so if I get you correctly, if let's say the joint is rotating, only rotation, it is a full joint, and also
Yeah.
only sliding is also a full joint.
Yeah. But if we
Okay,
have a
and
scenario where that mechanism is exhibiting both of them, then we say it is what? A half joint.
okay, sir.
It's clear
So
now.
then it means that it means that the half joint it can act as a full joint, right?
Let's say the half joint is combining the two types of what? Full joints that we have into one. You see. Mind you, we said that if the mechanism allows for only pure rotation, then we have what we call a revolute or what? Pin or hinge joint. All of them are the same. But if it allows for only sliding, then we have what? A sliding joint. You see. But that half joint combines what? Both the revolute and then what? The sliding joint. You see the difference? At the same time, yeah.
Okay, so we classify the joint depending on the mechanism, what is happening.
Yeah, depending on
right.
Yeah, we can that way. Depending on what the joint is doing. That's why we said a cam and a GI. When we move forward, we look at what a cam is and what a GI is. Then you actually know what is happening.
Okay, sir.
Yeah. Any other question? Yeah. So let's move on to what we call a linkage. We say a linkage is a mechanism where the links are connected to form a chain with one of the links what fixed. You see. And we also define a mechanism as what? Connection of what? Rigid links to perform or transmit what? Motion or a force. So if we have a mechanism where one of it is fixed, then we say we have what we call what? A linkage. Now the fixed link is called what? A flow, because it exhibits what? No motion. And it serves as the reference for the motion of all other parts. Yeah.
Yes, sir, please. Wanda was asking a question that is the actuator the energy producing component or the rotation producing component?
We say the actuator is the energy, the one that produces the energy. You see.
Okay, so it means that any component producing the rotation in the mechanism is not actually the actuator.
Yeah, you see that energy will be transferred to the links. So the links are the ones that are going to produce what that rotation, sliding, and all those things. You understand?
Yes, sir. Yes, sir. Please.
Yeah, you see. So that component that is producing the energy itself is what we are calling the actuator. Now, those who to what rotate, slide to give the desired motion are the ones that we are calling the links. You see, and the links too must be joined together by what we call joints. You see.
So please, can we call the crankshaft an actuator?
The crankshaft we can say is an actuator. The crank or the crankshaft, we have two different things. We have a crank and then the crankshaft.
Oh, okay, sir.
So we said that that's why when we were defining an actuator, we said that the crank here can be called as what? An actuator. You see. So if we are talking about a crank, then we can say the crank is what? The actuator. But the shaft itself is not an actuator. You see the difference?
Yes, sir.
So we have a crank and then we have what? A shaft. So the shaft of the crank is what we call the crank what? Shaft. But the crank itself is the one that we are calling what? The actuator. But the shaft is not what? The actuator.
Okay, sir.
Okay. So we say for a linkage, it's a mechanism where rotor links are connected together to form what? A chain. You see, so if we look at figure 4.2, for instance, this one we are calling what? A slider crank what? Chain. You see, the component one are the what? Fixed what? Points or fixed mechanism. So these ones are called what? The frame. Now component 4 is the slider. It is sliding on what? Component 1. And then component 3 is called what? The connecting rod. And then component 2 is what we are calling what? The crank. So this is a what? Kinematic diagram of what? An engine. The crank rotates, and when the crank rotates, it causes what? Component 3 to what? Oscillate. And because component 4 is fixed, component 4 will begin to what? Slide back and forth. So you realize that it will be moving back and forth, back and forth, back and forth. Now, an example of a linkage is the slider crank mechanism, commonly used in what? Petrol engines or internal combustion engines. So if you look at your vehicles, then we have a mechanism that we call a slider or crank mechanism there. Without that mechanism, there's no way the vehicle can move. So we say figure 4.2 shows you the skeleton outline of the slider crank mechanism. Link 1, 2, 3, 4 are what? The fixed frame, the crankshaft, the connecting rod, and the slider, which can also be called what? The piston, respectively. So we say in a 4-stroke engine, the piston is pulled down by the cylinder. Down the cylinder by what? The crankshaft, admitting the air fuel mixture. And then in the compression stroke, the piston is driven back up the cylinder by what? The crankshaft to compress what? The fuel air mixture. However, the rules changes in the combustion stroke when the piston drives what? The crankshaft. Then finally, the exhaust stroke change again as the crankshaft drives what? The piston back to expel what? The fumes. So basically, we say when you pick an engine, we have 4 main words. That is the intake stroke, the compression stroke, the combustion stroke, and then the exhaust stroke. Those ones you look at them in internal combustion engines, but let's briefly look at what we mean by the intake stroke. So realize that in your vehicle we have fuel, you see, and we also have air. So the intake stroke is where the piston comes down. So when the piston comes down, the inlet valve will open for the fuel to enter the cylinder, you see. Now, when the fuel enters the cylinder, then we have what we call the compression stroke. So the compression stroke will ensure that the air fuel mixture is compressed out to a particular pressure. When that temperature is reached, then we have what we call ignition. The igniter will just introduce a spark. And so when we have oxygen and then fuel mixing, and there's a spark, then combustion will take place. So when that combustion takes place, it releases an energy, and that energy will just push the piston down. You see. And if the piston is pushed down, the crankshaft too rotates. And now when the piston pushes down, that energy is released to the crankshaft, and the crankshaft will rotate. And those crankshafts are connected to the wheels. You see, so if the crankshaft rotates, then the grease tube will start rotating, and the vehicle will move forward. And then we have the last one, which is the exhaust stroke. Now, after the piston has gone down, the piston again moves up. So when the piston moves up, it will then push the combusted gases. You see, when there's combustion, we have some residue in the cylinder. So that movement of the piston will push the combusted gases out of the cylinder through the exhaust, and then the cycle is complete. Now that cycle will be repeated over and over again. You see, it will be repeated over and over again, and it's at a very quick speed. That's why the tire of the vehicle can rotate at a very high speed. And that speed, we are talking about 500 RPM and over. So that is basically what we mean by the slider crank mechanism. On Friday when we meet, I will show you a typical example of what a slider crank mechanism. And then we'll quickly look at what I have explained here. Practically what we mean by the intake stroke, the combustion stroke, the compression stroke, and then what? The exhaust stroke. Another type of linkage is what we call the 4-bar chain. A 4-bar chain is what is shown on the right-hand side of the slides. The 4-bar chain consists of 4 links, with link 2, 3, and 4 being movable as link 1 is fixed. So anytime you see a line with inclined lines beneath it, then we say those ones are fixed. Then link 2, 3, and 4 are now movable. So figure 2.3b shows the 4-bar chain operating as a double lever mechanism. And an example of a double lever mechanism is what we call the windscreen wiper. Those of you who have seen the wiper of a vehicle, you realize that it moves side to side. The mechanism that is driving that windscreen wiper is what we call
the 4-bar
chain.
chain.
4-bar chain, or the double lever mechanism. You see. So link 2 and 3, of which the lengths are constrained so that they can only oscillate backwards and forward. So whereas that we're moving side by side. And we say a practical example is the windscreen wiper. Other examples of linkages are the ratchet mechanism. The ratchet mechanism we say restrict motion in one direction. So we say if maybe you want the mechanism to only rotate in the clockwise direction, then the ratchet mechanism is the best option. And then we also have the quick return mechanism. That one is used in the shipping machine. Workshop technology. When we go to the workshop, I will show you the shipping machine and what we mean by the quick return mechanism. And then the spot yoke mechanism. That one we say convert a rotary motion to a linear motion. All those ones, if I'm you, I'll quickly go to YouTube and then type maybe a windscreen wiper, mechanism for a windscreen wiper. It will show you a video of how that mechanism is operating. That one will help you to understand everything practically. The same thing for ratchet mechanism, quick return mechanism, and then spot yoke mechanism. You can have a practical view of how they operate on YouTube. So just quickly type those ones there. Yeah. Hello. So just type those mechanisms there, and it will give you how they create in reality. That one will be much clearer than that one will make it much clearer. And then we have what we call the cam mechanism. And before we even move on to the cam mechanism, for the slider crank mechanism, you realize that we were saying link 1 is fixed. we can as well fix what link 3 and then we'll fix what link 2. Those ones will give us what different what mechanisms. We'll look at it when we move forward. Then we have what we call the CAM mechanism. We said the CAM mechanism has what we call a half what joint. We said it permits what sliding and then what rotation. If you look at this mechanism on the left hand side, you realize that this is what we are calling what the CAM, and this is what the follower. Where the CAM and the follower meet is where we are saying that there's what we call what a sliding action as well as what a rotation what action. Is someone selling goods somewhere or what? So if you look at this mechanism, the CAM is what is beneath here. So the CAM at this position is what rotating. And when it rotates, it has a point where the follower and the CAM will meet. At that point, you realize that because the CAM is rotating, there will be rotation at that point. And at the same time, because those two are meeting at that point, there will be some small sliding action there. That's why we say the CAM has both a sliding joint and then a rotation joint. Now we say the CAM is a mechanical component capable of transmitting motion to a follower by direct contact. Remember, as direct contact, then we expect that there will be some sliding action there. And because the CAM too is rotating, then there will be rotation as well. So the type of joint formed between the CAM shaft and the follower is called a half joint. In a CAM, the CAM is the driver, and then the driving member is called the follower. The CAM rotates at a constant angular velocity, and the follower moves up and down. So in this state, you realize that the follower will be down. Now, if this protruding end of the CAM begin to get in contact with the follower, then this protruding end will quickly push this follower up. You see. So as and when this end is in contact with the follower, then this follower will be pushed down. Now, the moment this end gets out of contact with the follower, then by gravity, the follower will just drop down to its original position. So in fact, this follower is just moving up and down, up and down, up and down. On the upward motion, the follower are driven by the CAM, and the return motion, they are driven by the action of gravity or a spring. So sometimes we mount what we call a spring here, so that if the follower moves up, then the spring would compressed, you see. Now, if the follower wants to come down, then that energy in the spring will just force the follower down because it will begin to release that tension in the spring. CAMs are used in many machines. For example, in the automotive engines, 2 CAMs are used per cylinder to operate the intake and the exhaust valves. You see. So whenever you pick an engine, just know that there's a CAM mechanism that is controlling the intake and the exhaust valves. That means that before the fuel can be admitted into the cylinder for combustion to take place, the intake valve must be opened by the camshaft. Now, after it has opened for the fuel air to be admitted, now it will close. You see. After the burning, then it means that the camshaft must also open the exhaust valve so that the burnt gases will escape the cylinder for new air fuel mixture to be admitted. For that to happen, the camshaft must open the exhaust valve. So the camshaft, the CAM mechanism is an important aspect part of the engine. Without it, the operation of the engine will not be smooth. So we have what you call classification of what? Mechanisms. Of CAM mechanisms. Now we say CAM mechanisms can be classified by their input and output what? Motion. We see the configuration and arrangement of the follower and the shape of what? The CAM. The follower configuration in Fig A to D are named according to their characteristics. So we say figure A is what? A knife edge what? CAM mechanism. Because if you look at this follower here, it is shaped as if it is what? A knife. That's why we are calling it what? A knife edge what? CAM follower. Now if you look at the B, you realize that the follower is shaped like what? A roller. So we say it is a what? A roller CAM what? Mechanism. And then if you look at figure C, the follower is shaped like what? A flat surface. So we say it is what? A flat faced what? CAM mechanism. And then if you look at figure D, the follower is shaped like what? A sphere. It has what? An oval shape. So we say it is what? It is called what? A spherical phased what? CAM mechanism.
Right on home.
So all those names are what? Separated from what?
No, but I go use bio the thing. Is it?
Hello?
Is it?
Can you hear me? Hello?
Oh, I really feel. Yes, sir.
You can hear me?
Sir. Yes, sir.
Okay. Because someone is saying he can't hear me. That's why I'm asking. So you realize that all those names are obtained from what? The shape of what? The follower. Huh? Now we also have other types which are what? The inline and then what? The offset. If you look at this one, for instance, the center line through what? The follower, and the center line through what? The CAM are what? In the same line. So we say those ones are what? Inline what? CAM mechanisms. The same thing for what? B. The center line are what? The same. C and D, the center lines are what? The same. But if you look at E carefully, you realize that the center lines have been what? Offsetted by what? A distance. If we have such a case, then we say that is what? An offset what? Follower. It is not in line with what? The center line of the what? CAM. So we say this type of followers are called what? An offset what? Follower. If you look at F2, you realize that the center lines are not in line. So we say they are called what? An offset what? Follower. So we say the center line of the offset follower does not what? Pass through the center line of the what? Camshaft. So basically, those are the two types of followers that we have: the inline follower and then what? The offset what? Follower. So we say followers are typically what? Spring loaded to maintain constant contact with the what? Shaped surface of what? The CAM. But gravity constraint is still an what? Option. Huh? But normally we don't want the follower to what? Drop by gravity. We want to have control, right? So we normally prefer the what? Spring loaded. So the spring will what? Control the movement of what? The follower. Any question on the CAMs before we move on to the GS? Hello? Hello?
Hi.
Yeah, I'm asking if there's any question on the CAMs before we move on to the GS. Okay, if there's no question, then we say GS are used to transmit what? rotary motion and power from what? One shaft to other with a constant angular velocity. GS have the advantage of producing what? Positive drive without slipping, and permits what? High torques to be what? Transmitted. Furthermore, GS are adequately indicated to operate at remarkably what? High efficiency over wide world speed range. GS can be used between shafts that are parallel or inclined towards each other. And when GS are in mesh, we say the bigger one is called what? A wheel, and the smaller one is called what? The pinion. So basically, when we say you want to transmit what? Rotary motion or power from one shaft to the other, then the most efficient one is what we call what? The GS. Even though we have a belt and pulley there, but the belt and pulley we say have some losses. It is not as efficient as what? The GS. Because with the GS, there's nothing like what? Slipping. But with the belt, we have what we call what? Slipping. And that slipping reduces what? The efficiency at which what? The motion can be what? Transmitted. And then when we want to transmit high torques to, we say we go for what? GS. And then another advantage is that whether the shaft are parallel or inclined, you can go for what? GS. But with the pulley and belt, that flexibility is not what? Available. So GS are very, very important when it comes to what? Transmission of what? Rotary motion. Now, this is what we mean by parallel shaft, inclined shaft, and the what? Non-intersecting what? Shafts. So these are examples of GS in what? Mesh. In some cases, the desired rotation in angular velocity is too great. And to achieve using only two GS, several GS are connected to give what? A geometry. And you will say that GS can be used to transmit what? Higher torques. In cases where these are very huge, you can't only use your two GS, you must combine the GS. So we can have as many GS as well possible. And that is what is used in the word gearbox. If you pick a gearbox, you realize that it has so many GS in what? Mesh. Because maybe the torque or the speed is very high, and the speed that we need to drive the mechanism is what? Too low. So you see, for us to achieve that, we use the GS to what? Reduce the speed of what? The speed that is coming from the actuator. And the actuator can either be an engine or it can be what? A motor. So if the speed coming from the motor or the engine is too high, then we use what we call a gear reducing what? Gearbox. We reduce the speed up to the speed that we want. If that is done, then we can actually what? Use it for driving our mechanism. Or sometimes to realize that the speed we require is what? Higher than the speed that the actuator is producing. That means that we need what? A speed increasing what? Gearbox. You see, so as to increase what? The speed. Now we have so many types of GS. And a typical example is the spare gear. And we say the spare gear is used.
Yeah, can you go big?
I said we have various types of GS, and a typical example is what we call the spare gear. And we say the spare gear is normally used to transmit motion. The previous slide.
Yeah.
Yeah, this is where I was saying it depends on what you want to achieve. If the speed that we want is more than the speed that the actuator is producing, then it means we must what? Increase the speed from what? The actuator. And with that one, we use what we call what? The increasing gearbox. That one will increase what? The speed. Now, if the speed from the actuator is what? Less. The speed that we want is less, and the speed from the actuator is what? Too much or too high for our mechanism. Then we use what? A speed reduction or gearbox. So that speed from the actuator will be what? Reduced up to the speed where we can what? Use. Then we what? feed that speed or that power towards our mechanism. And then basically we have so many types of gears.
Please, someone wants to join.
Oh, I've admitted all of them now. So we say the spare gear is used to translate what motion between what two power shafts. So for instance, this figure you realize that if this is the shaft, if you draw a line through the axis of the shaft, you realize that the center lines are what parallel to each other. If we have such a case, then the best option is what we call the spare gears. And then we also have what we call helical gears. You see, and that one is used to when we want to transmit motion at an acute angle rather than at 90 degrees. Rather than at 90 degrees. So if you look at this one, for instance, if I draw a vertical line through the axis, whether that angle does what? 90 degrees. Now if hey, too quiet. Who is that? So we say that teeth of the helical gears are cut at an angle rather than parallel towards the axis.
That boy, you're making noise.
And these ones help in reducing the noise. And also helps in having what? Hey, those talking. Who are those?
Can you please mute all of us?
That boy, you're making noise.
And you're mute.
Yeah, so if we want a reduced noise, then we say we go for helical gears. If you want a smoother drive, then we say you go for helical gears. And then if you want your gears to have a prolonged life, then we go for helical gears. As well as driving heavy loads. Because these teeth are mentioned at an angle rather than less than 90 degrees. So we say this helical gears produces what we call an axial force component on the shaft bearing. So in order to overcome that, then we have what we call a herringbone or double helical gears. So if we have such a mechanism, then it means that the teeth are cut opposite to each other. So those forces will cancel out because if one is positive, the other one will be negative. So they cancel out, and then we eliminate the axial force component. And normally we have spoken about trains. If we say gear train, means that we have a number of gears in mesh, like in the gearbox. So we have a simple train, compound train, reverted train, and then epicyclic trains. A simple train, we say it has only one gear. It's called the simple gear train. So if we have 100 shafts, and each shaft is carrying only one gear, then we say we have a simple gear train. For gear A, it has only one shaft, and there's only one gear mounted on it. The same for gear B. For this one too is the same, and those ones in 3D form. This is how it looks like. And we say for compound train, that one we have at least 2 gears mounted on one shaft. So if you look at this shaft A, it has only one gear. But if you look at shaft B, it has 2 gears. That is gear C and then gear D. And then if you look at shaft B, it has only one gear. And this has been shown in this figure here. This is shaft A, 1 gear. Shaft B has 2 gears. One of it is meshing with B. The other one is meshing with A. And then shaft B also only one gear. So if we have such a case, then we say we have what we call a compound train. And then we have an epicycle or planetary train. And this is where there's relative motion between what axis of the shaft. In this gear train, one or more wheels is carried on the arm, which can rotate about the main axis of the train. Such wheels are called what? Planets. This one rotates like the planet and the sun, you see. The planets are revolving around what? The sun. At the same time, the sun too is also what? Revolving. That's why we call them what? The planetary what? Gear trains. So if you look at the solar system carefully, I think those who invented this one looked at the solar system, how the solar system operates, and then they use that same knowledge in designing what? The planetary what? Gear trains. And if we talk about compound planetary gear trains, then it means we have a lot of them in what? Mounted in the mechanism. So we have hello. Yeah, so we have that multi-stage mechanism shown on the right-hand side of what? The slide.
Hello, sir.
Yeah, hello. And we have functions of what? Planetary gears. The first one is they provide what? A higher torque capacity by using what? Multiple planets. And the second one is they have higher gear what? Ratios. That can only be achieved. And they also provide variable or gear ratios, and they are compact in space what? Requirements. And both static and dynamic forces are balanced if multiple planets are what? Used. These are the various advantages of having what? Of using planetary gears. And then some engineering applications are tractor and construction equipment, where there's automatic transmission in automobiles, bicycles for controlling what? Power, and then powertrain between what? Internal combustion engines and an electric what? Motor.
Sir.
Yeah.
Hello, sir.
Yeah, hello.
Please, the gears, are they classified according to their functionality or the geometry of their respective teeth?
Normally, we look at the teeth for its classification. And then sometimes we even how the shafts are what? Mounted. You see whether the shafts are inclined to each other, whether they are at right angle, whether they are at what? Acute angle, whether they are parallel to each other. All those ones are the various what? Ways of classifying what? Gears.
Okay.
And then we have what we call the kinematic chain. It's used to specify what particular arrangement of links and joints when it is not clear which link is to be treated as what? The flame. To act as a kinematic chain and transmit motion, a kinematic chain might have what? One of its links what? Fixed. So when we see this symbol, then it means that is called what? A fixed what? Link. So you take note of that. So we say kinematic what? Invention. So if, for instance, one link is fixed, and then we decide that fixed link now we are going to make it unfixed. We are going to unfix it, and then we fix another link. Then we say we have done what we call invention. So in the use of mechanism, a link which was originally fixed is allowed to now to move. Another link becomes fixed. Then the mechanism is said to be what? Inverted. The invention of a mechanism does not change the motion of its links relative toward each other, but does change their absolute motion relative toward the ground. So kinematic invention are different mechanisms obtained from the kinematic chain by fixing the various links of what? Mechanism in turn. So an n-link kinematic chain will produce what? An n different what? Mechanisms. Most mechanisms can, yeah.
Can you repeat the kinematic chain?
Okay. So most mechanisms can be reduced to two basic kinematic chains, a 4-bar chain and a slider crank chain. So we say for kinematic chain, for instance, if you look at this mechanism, for instance, if let's say link 1 here is what? Fixed. Now, if I decide that this link 1, I will no longer fix that one, but I will now come and fix link 4. You see, then I will obtain what? Another what? Machine that we are calling what? The kinematic what? Chain. We will obtain another machine which is different from what? The one that we have here. Because the output now will also change. The motion of that machine will change if we change the phase link from one link towards the other. So for instance, this one has 4 links. So that means that I can fix 4 different links. That's why we said an n-link kinematic chain will produce n different mechanisms. You see. So if I fix the various mechanisms, I will have different mechanisms being produced. That is what we mean by a kinematic chain. Now we also have what we call degrees of freedom. The degree of freedom of a body gives an indication of number of independent variables assigned for measuring or determining the type of relative motion permitted at a pair. So degree of freedom, we say how can the mechanism move? So the body can rotate in 3 different independent directions and 3 degrees of freedom. If we look at this mechanism, for instance, in the Z direction, we say there is rotation. In the X direction, we say there is rotation. And then in the Y direction, we say there is rotation. So we say this mechanism here has 3 degrees of freedom. This one too has translation in the Z direction, translation in the X direction, and then translation in the Y direction. So if we combine these two, then we say the mechanism will have 6 degrees of freedom. Because there will be both rotation and translation in the Z direction, both rotation and translation in the X direction, both rotation and translation in the Y direction. So if we put all of them together, we get 6 degrees of freedom. Now, how do we calculate degrees of freedom? So the mobility of a mechanism is the number of degrees of freedom. How mobile a mechanism can be determines the degrees is what we call degrees of freedom. So how do we calculate that? We use what we call the mobility criterion. And that formula is M is equal to 3 times N minus 1 minus 2J1 minus J2. So what is M, what is N, what is J1, and what is J2? M we say is the mobility or the number of degrees of freedom. N here is the number of links. And then J1 is the number of degrees of freedom joints. And then J2 is the number of degrees of freedom of half joints. So you see, we have already discussed half joints and full joints. So we are going to apply it in determining the mobility of a mechanism. And in determining the mobility of a mechanism, we say care must be taken when applying the equation because there are a number of special mechanism geometries for which it will not work. So if you look at this mechanism, for instance, we said that M is equal to 3 times N, where N is the number of links. So if I count this mechanism, I have 1, 2, 3, 4, and 5 links. Because link 1 here, this is link 2. Link 3, if we see this joint here, it doesn't mean that this is one link, this is another link. All these ones are classified as one link. This one is another link, this one is another link. So we have 5 links. Now, the J1 is the number of 4 joints. If you count them, we have 1, 2, 3, 4, 5, 6. So here we have 1 joint here because there's a connection between link 2 and then link 1. A connection between link 5 and then link 1. A connection between link 4 and then link 1. This one, 2, 3 and 4. 5 and 3, and then 2 and 3. So wherever we have 2 links meeting, we count it as a full joint. Now we said that J2 is half joint. and half joint is formed between what? Cams and then what? GS. We don't have any cam here, we don't have any GA here. So that one goes to what? 0. So if we calculate this one, we get M to be equal to 0. But nevertheless, this device actually moves as a result of its special geometry. And it's a mechanism with what? 1 degree of what? Freedom. So we say it's not all the time that the mobility criterion works. Sometimes that formula ceases to what? Function. And an example of that is this mechanism that we have shown here. Now, in determining the joints, we say a point connecting what K links to a single joint might be counted as what? K minus 1 what joint. So if I take this one, where K is what? K is the number of what? Links here. So if I take this joint, for instance, we have 2 links. That is link 2 and then what? Link 3. So K is equal to what? 2 minus 1, which is what? 1. That is why we counted it as 1 when we were calculating the mobility. We do the same for all the joints as well. So if M is greater than 1, then the device is a mechanism with what? M degrees of freedom. So this mobility formula that we have here, after calculating for M, if we get M to be greater than 1, then we say we have what? Hello? Then we'll say we have a mechanism with M degrees of what? Freedom. If M is equal to 0, then we'll say that mechanism forms what? A structure. And we say a structure doesn't permit what? Motion. And if M is less than 0, then we have a statically indeterminate what? Structure. So quickly copy this one as an assignment. When we meet on Friday, we'll quickly look at how we are going to apply this formula in calculating for the mobility of mechanisms. So we'll quickly go and then read it and try and understand what we mean by mobility of a mechanism. When we meet on Friday, we'll go through some problems together. And then we'll move on to kinematics, where we'll look at the analytical method as well. So we'll quickly write this one as the assignment of the day. Already I've given you one assignment on balancing. Hello?
Okay, so please when I taking this one.
So this one is 2 weeks from when you submit the one for balancing. Agreed.
So next 4 weeks.
No, next 4 weeks.
Yes, sir.
Balancing was Friday.
No, it's said 2 weeks after we have submitted the
balancing
so
one.
3 weeks. 3 weeks.
So this Friday
Next
is
3
1
weeks.
week.
Yeah,
The next
so next 3
Friday
weeks.
is 1 week. The next 2 Fridays, I will take this one. So we will look at these examples. How we will calculate what? The number of degrees of freedom of all these what? Mechanisms on Friday. So if you go, you can just try your hands on it. So that when we meet, we look at it together. Agree?
Agree.
Yeah, so we'll look at it so that when we meet on Friday, we look at it together. Any question?
Yes, I have a question.
Okay.
On the last slide before the assignment.
Okay. Yeah, this is the last slide.
Yes. So say the links, the link 1. No, where we have the image.
Yeah.
The one you've labeled link 1.
Yeah.
Is it because they are all fixed? We consider them as one, or like how is it classified?
All of them are fixed link. So we'll put all of them as one.
Okay.
Yeah.
Okay.
So by the time you see for link 3, for instance, it's starting from this edge here. and it ends at the other edge. So if I decide to draw one line here, then everything down here forms one link. You see?
Yes, sir.
Understood? So
Yes,
if
sir.
maybe because if that line comes, then everything here behaves as what? One link. In the same way, because this is one line, everything there was behaving as what? One link.
Okay.
Yeah.
Okay. So assuming if you had a fixed joint even between the upper line there, then we will have two links over there.
Yeah, maybe if we have another line here, then we have what? Three links. That is where the K minus one comes in. So it means that we have three links. You subtract one, then at that joint we have what? Two full joints there. So we'll no longer count it as one, but we'll count it as what? Two.
Okay.
You understand it now?
Yes, sir. Thank you.
Okay. Any other question? Okay, if there is no question, then we'll call it a day. I have another class at 12:30. So quickly go through what we have done today. And then when we meet on Friday, we'll try and apply the theories that we have learned today in solving problems. Don't go and put it down and come on Friday and be looking at my face.
Yes, sir.
Okay. So enjoy your day. We'll meet on Friday.
Have a good day too.
Okay.
Professor Ian.